When a gas is involved in a reaction, either as reactant or product or even both, we often will specify the quantity of the gas in terms of its volume at a particular temperature and pressure. So, doing stoichiometry with gases, we're going to use the ideal gas law to find the amount in moles. So if we have a volume at a given pressure and temperature, we use this version of the ideal gas law to calculate the number of moles. If we have the number of moles of gas and we're trying to find the volume that we're going to end up with, we would use just a different rearrangement of the ideal gas law. If this is occurring at STP, things become much simpler because then we can use the molar mass of a gas at STP as our conversion factor. So that makes things easier. But remember, this only works at STP. So here we have our basic stoichiometry path. Grams to moles to moles to grams. All stoichiometry calculations are just variations on that theme. Mole to mole is the same always, but the beginning and or the end can change. So we could start with pressure, volume, and temperature of a gas, go to moles, go to pressure, volume, and temperature of another gas. Or we could have mass here, or mass there, or we could have a volume of a solution with a known molarity. There's all sorts of possibilities. Do an example. This following reaction, 4.58 liters of oxygen, was formed at P equals 745 millimeters mercury and T equals 308 Kelvin. How many grams of Ag2O silver oxide decomposed? We have a chemical reaction occurring. Let's use the equation to organize the information. So I'm told that there's 4.58 liters of oxygen, and the pressure is 745 millimeters of mercury, and the temperature is 308 Kelvin. Because if we want to know the moles, we need to specify the volume, the pressure, and the temperature. And the question then is, how many grams of the silver oxide decomposed to make that amount of oxygen? So our question mark, how many grams of that? So, stoichiometry, grams to moles to grams. Here we are looking for grams, so we want grams at the end. But here we're not given grams, we're given a pressure, a volume, and a temperature. So we've got P, V, and T of a gas, and then we can calculate moles. So this step is using the ideal gas law, and once we have moles of oxygen, then we can use dimensional analysis to finish it out. N equals PV over RT. So pressure. It's given in millimeters of mercury. Well, that'd be 745 over 760 in atmospheres. And the volume was given 4.58 liters. R is always the same, 0.08206 liter atmospheres per mole Kelvin. And the temperature is 308 Kelvin. $745 divided by 760 times 4.58 divided by 0.08206 divided by 308. Let's move down so we have some more room. 0.17763 moles of oxygen. Any questions yet? I have now reached this point where I found moles of the first thing. So now I'm going to convert that to moles of the thing I'm trying to learn about, the Ag2O. So I'll divide by moles of O2 so that the units cancel out. And then here I want to get grams of Ag2O. So I divide by moles of Ag2O. The mole ratio comes from the balanced chemical equation. 2 moles of silver oxide give us 1 mole of oxygen. So it's 2 moles of silver oxide for every 1 mole of oxygen. And then here I need the molar mass of silver oxide. How to calculate that? 2 times 107.9, right? Yeah. Plus 16. 231.8. That's the mass of 1 mole of silver oxide. 231.8 grams for every 1 mole of silver oxide. So I've got my number of moles times 2 times the molar mass, 82.351. 3 sig figs grams. Rounding gives me 82.4 grams. Any questions? They could tell us that this volume of oxygen was collected over water at this pressure and make us go look up the vapor pressure of water and subtract that off. There's just so many different things you can do with this problem. Let's do another one. This is one at STP. These magic letters. How many liters of oxygen at STP are required to form 10.5 grams of water? This makes the problem much easier. So 10.5 grams of water, write that in there. And the question is, how many liters of oxygen, question mark, liters at STP? Because it says at STP, I can use 22.4 liters per mole. Otherwise, you can't. So, grams to moles to moles to grams. That's a great starting point for any of these. So here, I've got grams that I'm starting with, but I don't want to end up with grams, I want to end up with liters. So I'm going to end up with liters at STP. So the molar volume of a gas is the conversion factor between liters and moles at STP. .5 grams of water, and I'm going to convert that to moles of water, and I'm going to go to moles of the thing I'm looking for, moles of oxygen, and I'm going to go to liters of oxygen. I figured all that out in my path up here, grams to moles to moles to liters. Grams to moles to moles to liters. I put the previous unit in the denominator, so those units cancel out. This is a little bit like when you make a mistake in your lab notebook. And we can see that I've crossed that unit off, but we can also very clearly see what the unit was. We want to be able to see what it was that we crossed off. All the units in place, I like the mole ratio first because it's easy. 1 mole of oxygen gives 2 moles of water. 1 mole of oxygen to 2 moles of water. This one here, liters per mole, that's sneaky. That's that molar volume of a gas. So any gas, 22.4 liters per mole at STP. So that's going to be 22.4 liters per mole of oxygen. And then I need the molar mass of water, which I use so much that I memorized it. Not intentionally, just, can't forget it for the life of me. 10.5 divided by 18.016 divided by 2 times 22.4. We should have 3 significant figures. So 6.5275 liters. And we would round that 6.53 liters. Any questions? That's the polite Amtrak train.
Should we memorize the 22.4 liters?
You should memorize the 22.4 liters per mole. You could calculate it if you forget what it is, but that kind of defeats the point of using it. But you can calculate it. You just put in 1 mole and standard pressure 1 atmosphere and standard temperature 273 Kelvin, and calculate the volume and you'll get 22.4.